Hi, my name is Caitlin Malik. I will be reviewing Lenz's law, or right-hand rule number 4. Today I'm just gonna start off by kind of going over like definition type things and OneNote, and then we'll kind of go into two larger examples that will hopefully help better your understanding of this right-hand rule. So first off, Lenz's law means that the current produced by the induced EMF moves opposite in direction to the original field. So you can kind of, keynote is the original field will be known as your external field, and then your induced field or your induced EMF will be the internal field. And you want those to oppose each other, and we'll kind of dive deeper into that. But the biggest thing is you want the EMF to oppose each other, because if the flux isn't opposing each other, then it kind of harms equilibrium. And a big thing about this law is that the internal environment of the magnetic field and the external environment of the magnetic field need to kind of work together to have like a neutral environment, be in equilibrium. And then a goal is to determine whether the current needs to flow counterclockwise or clockwise in order to oppose the field. And so again, my examples will hopefully help kind of solidify these two things in your mind. And then just a general note, we discussed this briefly in class, but I wanted to point it out just in case you forgot. Lenz's law, or the right-hand rule number 4, actually explains the negative sign in this equation. So that'll be important, and that negative sign basically represents how these need to be opposite in direction. So if you take anything out of this video, know that the fluxes need to like oppose each other by using the internal and external magnetic fields in order to create like a total zeroed out equilibrium overall environment. Okay, so for our first large scale example, this is going to represent a wire or a coil, and then this represents the external magnetic field. So as you can see, they're dots, so that means that the magnetic field is coming out at us. And so basically what we want to kind of summarize before we go into the actual finding like the current flow and the overall movement and direction is that the inside magnetic field will increase as a result, and so will the magnetic flux, and that those two things have kind of a direct relationship. So as one increases, so will the other. And you know that the magnetic field will increase because it's going to be impacted once it moves with its velocity towards this external magnetic field. And then the induced EMF will then make a current that will create a magnetic field that will oppose the external magnetic field. So if this is coming out at you, what magnetic field will create a current that will have that homeostasis balance, that neutral balance that will allow it to just have like kind of like a no charge kind of zone. So I kind of drew this larger scale. So again, this is going to represent kind of like a 3D. It's just like a string of that coil that we discussed. And then this expo marker is going to represent this side right here. So I'm going to actually kind of dot that out for us. And then, so if you kind of like look at this picture here, I kind of just dotted around that segment, and that's the same segment here, and that will be represented by the expo marker. So if you look at the expo marker, this is coming out at us like we talked about, and so then in order to oppose it, then you know that the inside has to be coming into the board. So because this is going out, this has to go in, and so that's key in finding the current. So if you look at this and you line it up, your fingers need to go in the movement of that magnetic field. So it's going out right at us because of those dots, and then it's coming back in once it hits the coil. It's going to come back in, so it's going this way. So then your thumb is going to give you the answer. because whatever direction your thumb is then shows the current. So because we're moving this way, your thumb, as you can see, I don't really know, my arm is really bending here, but it is pointing down. So you know your current flows in a downward direction, so it'll go this way. So it's going this way. And the same will also apply for all of these segments too, because the magnetic field on the outside remains the same. They all remain coming out at us. So the inside will all remain coming towards the board. So then again, you could do the same for any of these, and you're all going to get the same result of they're all going to go this way. And then I'll make this one pink just to kind of coordinate. And it's kind of, this is a 3D one, so I can't like literally draw over the string. But in summary, if you need to see this, basically we're saying that this is coming out at us at the outside, and therefore in order to have that neutral balance of the magnetic field, this has to be coming into the board, and so therefore the direction of the current, which was demonstrated by when we use the expo marker, will be going this way consistently. And this way mirrors how a clock works, so the overall movement and direction will flow in a clockwise direction. Okay, so for this example, it's going to be a little bit different than example 1 because your coil or your wire, whatever you prefer to call it, is already in interaction with the external magnetic field, and it's actually, its velocity is moving away from it. And so when this happens, your external field is going into the page, and so therefore your flux is decreasing because of that movement away from it. And then in turn, you can kind of look at this as if the flux is decreasing because of this, you want to counteract it with something, because again, we want that equilibrium. So if your flux is decreasing, then you need a flux that's increasing. So what environment is going to create that? And it's actually going to be created by making your internal environment the same as your external environment, because those will create the increasing flux as opposed to the decreasing flux. So because this is going into the page, the internal environment will also go into the page. And so once you figure that out, once you figure out the relation between the external and the internal environment, you're good. You can kind of disregard this external field for right now. And then you kind of need these on the outside of your redraw to be opposing the x's, because you have to have that current be shown. If they were the same thing, there would be no current. So if you look at this segment right here, this is again going to be represented by the expo marker. So if you line it up, your outside environment is going to be going out of the page, and then your inside environment, once it hits this expo marker or this edge of the coil, is going to go into the page. So again, you're going to have the same movement as we did for example 1, and your thumb, which represents the current that is being created by this magnetic field, is going to be facing downwards again. And so when it's facing downward, it'll go in this direction, so that way. And then these are all the same kind of environments. You could practice on your own, kind of doing this with your hand to kind of get the magnetic field to match up and the currents to go the right way. But overall, this is going to have the same movement, and so it's going to be in the clockwise direction. So I don't know if you guys caught it, but example 1 and example 2 show different things in the fact that in example 1, because the external environment wasn't initially being interacted with this coil, the flux is actually increasing. And so when your flux is increasing, you want it to then decrease so that it opposes it and that equilibrium is met. And so the magnetic field will be in the different direction. So remember how this was going out of the page, and so we had to make this go into the page. So that's kind of like the difference. If it's not in contact with the external magnetic field, the external magnetic field and the internal magnetic field will oppose each other. And then in example 2, the coil or the wire is already in contact with the external magnetic field, and so your flux is decreasing. And so in order to have it increase, to kind of, again, have the equilibrium between the magnetic field environments, you'll have to have it be in the same. So this is going into the page, and so your external environment matches your external, and they both go into the page. And so that's just a very key concept for knowing the right hand rule number 4.